In this video, we'll talk about the opposite direction, converting equations from polar coordinates back into rectangular coordinates. This process can be a little more tricky because of how the equations look. There's a couple things to keep in mind when you're trying to do this conversion from a polar equation in the form of r equals f of theta into something in terms of x and y. And the main thing is you want to look for good terms in your expression. What do we mean by that? We mean things like r sine theta, r cosine theta, r squared, things that go into nice when you convert them into x and y. So these are things like r sine theta, r cosine theta, r squared, tangent theta. Right? Sine or cosine by itself is not great because you have to divide by r and you divide it by a square root, and that gets kind of nasty. If you can make it have these terms first before you try to convert, that'll make your life a lot easier. So you want to manipulate to get as many of these good terms as possible before you try to convert into rectangular coordinates. In the example here, we'll showcase what that looks like. So I want to convert the polar equation r equals 4 sine of theta into rectangular coordinates. So I could try to plug in right away, but that's going to get kind of annoying because I have a square root somewhere and some weird denominators and stuff, and I don't want to deal with that. What I can do instead is we'll multiply both sides of this equation by r first. Multiplying by r, we'll get r squared equals 4r sine of theta. Now that looks a lot better because I like r squared and I like r sine of theta. Let's take that and now let's convert this into rectangular coordinates. We know r squared is x squared plus y squared, and we know r sine of theta is y. Now let's see what this looks like by simplifying things out. So I can move that to the other side. X squared plus y squared minus 4y equals 0. And to make this look nicer, I want to complete the square. To do that, I need a plus 4 over here and a plus 4 over here. So then I get x squared plus y minus 2 quantity squared equals 4. And what's that shape? That shape is a circle of radius 2 centered at the point 0, 2. So again, for comparison, we have this in rectangular, and we have r equals 4 sine theta in polar coordinates. I would argue this function here is a lot simpler than the one we have in Cartesian coordinates, because there's no squares, there's no weird combination, and I also have r as a function of theta here, where I can't write this as y as a function of x in Cartesian coordinates. It's a circle, I have a top and a bottom part to the function, so I can't write it all as one function. In polar coordinates, though, I can. I can just write r is 4 sine theta, and that covers it for all values of theta for all values of r. That gives me my equation. I don't have to worry about splitting based on what I want the top and bottom part of the curve. So that is the main reason why we like polar coordinates in this circumstance. It gives us a nice way to write this equation as a single function without having to worry about the top and bottom halves or the weird square roots that come about when you're trying to solve up for circles. So that's what you want to keep in mind when you're looking at converting equations from polar coordinates back into Cartesian coordinates, is the fact that it's a lot more helpful if you look for the good terms first and try to manipulate your expression to make as many good terms as possible, things like r squared, r sine theta, r cosine theta, before you try to convert them. If you try to convert them too early, you'll wind up with a complex expression that becomes hard to figure out what the function looks like. But if you do the good steps first, you'll be able to get this pretty easy to sort out what the function looks like based on its polar coordinate equation.